and then you can design circuits. Our task today is relatively easy. Chapter 9. Everyone has previewed this chapter. It mostly contains conceptual concepts that you already know, and then you can design circuits. Just design it according to his instructions, so we're relatively relaxed. We only need to explain the things that might be misunderstood or not, and then emphasize some points that might be overlooked. Okay, let's begin. The first section is about drive circuits and light industrial circuits. We're already very familiar with them because we've done 3 experiments, each of which included drive circuits. Everyone has a clear understanding of what they do and what functions they perform. So, what I want to emphasize here are the things that might be overlooked. One is the second sentence mentioned here. The drive circuit is crucial. It's not just about amplifying power and transforming the low-current signal from the control signal generator into a high-power bulb that can be turned on and off by the power electronic device's control terminal. It's much more than that. In fact, after reviewing this chapter, you'll understand that there are specific requirements for the waveform of the signal applied to the control terminal of any electronic device. When these ideal waveforms are met, the tube operates in a more ideal state. Ideal here refers to 2 main points: shortening switching time and reducing switching losses. Conversely, as we discussed in Chapter 8 about soft switching, we've already mentioned that switching losses occur during the switching process, and changes in voltage and current waveforms during switching can also lead to switching noise and electromagnetic interference. Here we want to emphasize the design of the drive circuit. The quality of the drive circuit is directly related to the 2 points mentioned earlier: electromagnetic noise and switching losses. Often, it's not the power electronic devices themselves that are at fault, but rather the poor design of the drive circuit, which can exacerbate these 2 problems. Secondly, I hope everyone will pay attention to a point mentioned in the textbook. The 4th protection measure mentioned here is because the drive circuit is directly connected to the power resistor. The switching operation of the power electronic device is directly controlled by the drive circuit. Therefore, when considering how to quickly protect power electronic devices, the most expensive and easily damaged devices in power electronic circuits, the most effective and fastest protection measure is to implement protection in the drive circuit. Which is closest to the power electronic circuit after the control circuit. This is the fastest and most effective protection. In experiments 1 and 3, we use the IR2110 and I22010. As you all know, to make it work on the experimental circuit board and generate an output signal, you need to insert a jumper. What does that jumper change? It changes the voltage level of an input pin, 11-pin SD, of the IR2110 chip. Okay, so what does the SD tone do? Now, if you wipe the jumper and don't plug it in, does its output have a signal or not? When there's a signal, the circuit is working. When there's no signal, what does it mean? It means blocked. It means the main circuit isn't working. It means all power electronic devices in the main circuit are in an off state. This pin is for this purpose. It's not for jumper design in our experimental setup. It's designed for protection. For example, in power electronic circuits, if power electronic devices are to be damaged, the main direct cause of damage is overheating. This is the primary cause, and overheating is caused by excessive current. Therefore, power electronic main circuit designs often include temperature measurement to measure the temperature of the device or heatsink or overcurrent protection. So, whether you're measuring temperature and setting a threshold, saying something happens if the temperature exceeds a certain threshold, or measuring current and saying something happens if the current exceeds a certain value, what's your action after this? Greater than signal? This greater than digital signal is directly connected to the SDN pin, directly causing the I22110 output to be shut down, and your entire main circuit to stop working. This is the most effective and direct measure, and please pay attention to this point. Next is isolation. In fact, we already discussed this in section 2.1 using this slide, so there's no need to repeat it. Just remind everyone to pay attention to the internal structure diagrams of the 3 different official chips given in the textbook. What it's actually talking about here are 2 things. First, optocouplers. Optocoupler chips also have different speeds. What is speed? We've already discussed that before. There is always a delay between the input and output of a signal in any integrated circuit chip. Optical couplers, because they rely on light to transmit information, typically have a longer delay than those in traditional integrated circuit chips, which do not use light. Therefore, in circuit design, the speed we need to consider is directly related to the frequency of the signal that an optocoupler can effectively transmit. In power electronic circuits, the most common application of optocouplers is to achieve isolation between the control circuit and the main circuit. In such cases, the optocoupler chip is typically used to transmit PWM control signals. The frequency of the PWM control signal is the switching frequency of the transistor, for example, about 20 kHz in our experiment 3. So, to synthesize such a signal, what do we generally mean by this frequency when referring to an optocoupler? The optocoupler has a delay time, and this delay time should be less than 1/10 of the period of the signal you want to transmit. This is the minimum requirement. A better scenario is within 1% of the period of the transmitted signal. Secondly, regarding BO, these 3 different graphs tell us what the transfer ratio is. The transfer ratio refers to the current. The chip has an input current, marked as IB here, and an output current, marked as IC here. Dividing the output current IC by the input current IB gives its transfer ratio. In fact, it's the current amplification factor. This amplification factor can be much smaller than 1 or much larger than 1. This is what the textbook refers to as high or low transmission ratio. In experiment 2, we used an optical network chip and a CPL3340. Its output current measurement can reach the ampere level and can directly drive a MOSFET. This is considered high transmission ratio. However, if, as mentioned earlier, you are only transmitting a PWM control signal, and then the control signal output is connected to a driver circuit for amplification, then a low transmission ratio is better. Often, the higher the transmission ratio, the greater the speed, which is what we just discussed, the transmission delay, and the lower the speed. I'm saying often, not absolutely. Some chips balance high transmission ratio and high transmission speed. Okay, that's a brief overview of optocouplers. Next, we'll look at the specific driver circuit. The textbook's order for driver circuits follows the sequence from Chapter 2, when we introduced these devices: thyristors, then GTTR, and then SIGBT. Regarding thyristors, I want to reiterate that their driver circuit isn't called a driver, but a trigger. Only thyristors are called triggers. All other components are called drivers. Don't use the wrong terminology. In recent pre-class preparations, some students have said that MOSFET is a trigger and IGBT is a trigger. That's incorrect. It's called a driver. Pay close attention to this terminology. We may be more familiar with devices like MOSFET and IGBT because we use them in experiments, but you might be less familiar with thyristors, so pay even more attention to these descriptions. Here's something I want to remind you about. Please read this sentence carefully. What does it say? This is the original text from the book. What does this sentence mean? As we all know, the outdoor temperature varies throughout the 4 seasons of spring, summer, autumn, and winter. This sentence means that the operating environment and temperature of the power electronic device you design will affect your circuit design. If the circuit you design is intended for indoor use, the indoor environment is generally better, maintaining a temperature of around 25 degrees Celsius year-round. This is one design approach. However, if your design is intended for outdoor operation, such as mobile phones, which are designed for outdoor use and have a reasonable temperature range, then some phones, designed specifically for 25 degrees Celsius, will significantly underperform outdoors in winter. This is related. The concept here is that in winter, the trigger current you apply should be higher. What should we pay attention to in summer? In summer, we need to focus on heat dissipation. In winter, even a small heat sink will dissipate heat quickly due to the cold. In summer, it's hot, and we must ensure good heat dissipation to prevent it from burning out. Therefore, when designing this device for outdoor operation, the trigger current should be designed for winter, and the heat dissipation should be designed for summer. This way, it can function normally all year round. Next, we'll discuss the design of the thyristor triggering circuit. First, we'll look at the ideal trigger pulse shape. Here, there are some commonalities shared by all devices. Please note that initially, whether it's a voltage-driven type or a current-driven type, a relatively high pulse is always desired. This is called a strong trigger pulse. Then, the subsequent pulses become relatively smoother. This strong approach, with its initial high speed and rapid changes, is beneficial for device turn-on and shortens the turn-on time. This applies to all devices. Conversely, during the initial pulse, the thyristor is an uncontrollable device and doesn't require a specific type of pulse. However, all the other devices in the home circuit require a pulse. The pulses are often similar, starting with a large initial impact followed by a smoother one, which also helps shorten the turn-on time. This is a common feature. Now, let's see how to design our circuit to make it pulse briefly and then smoothly. As you can see in this circuit, the structure is actually very simple. As a drive trigger circuit, the back end is directly connected to the MOSFET and SPI, which is connected to the thyristor. The transformer added here is obviously for isolation. The primary side of the transformer is directly connected to the trigger pulse circuit invented by your control circuit. After the pulse arrives, it passes through two transistors. You'll see this is a Darlington transistor structure, connected in series. Why series? Simply to increase the amplification current. With these transistors conducting, current can flow through the transformer windings sequentially. This means that only when the front-end transistors V1 and V2 are conducting, current flows through the primary winding of the transformer, and the secondary winding will generate a pulse. The moment these two transistors conduct is the starting point of pulse transmission. The circuit structure is simple. Let's look at two small details below. First, the primary winding of the transformer has a resistor and a diode connected here. Why? Think about it. When V1 and V2 are conducting, if a current flows through a mouse and then it turns off, the current in the primary winding of the transformer should instantly drop to zero. However, the current flowing through the primary winding of the transformer necessarily means that there is a magnetic field inside the transformer. A magnetic field stores energy. If you don't provide a path for its release, the voltage across the winding will become very high, eventually causing it to break down. Therefore, when V1 and V2 are turned off, you need to provide a path for the energy stored in the primary winding to be released, so that the magnetic field of the transformer can dissipate the energy. That's why we have this diode and this resistor, which provide a path for the energy stored in the primary winding to be released when V1 and V2 are turned off. The energy is dissipated in this resistor. Of course, the smaller the resistance, the better. The more pronounced the consumption effect, the more obvious the suspected brain group voltage inhibition, and the safer it is. The second thing I want to talk about is this bone R2 and C1. You might notice that the structure is a bit strange. What is the purpose of connecting capacitor C in parallel with resistor R2? Consider that when V1 and V2 are not conducting, i.e. during the step pulse, if there was any stored electrical energy in C1, it would be consumed through R2 during this process. Therefore, at the moment V1 and V2 are conducting, the voltage across capacitor C is zero, indicating no stored energy. So, consider that at the instant V1 and V2 are conducting, as mentioned earlier, when it conducts, the upper part of the capacitor is connected to the power source, and the lower part is connected to the force source. Therefore, current will naturally flow. Due to the effect of inductance, the current will not increase to a large instantaneous value. And what limits it? It's limited by this resistor. Because of this resistor, the current won't be very large. But please note that at the instant V1 and V2 are turned on, the current flowing through this resistor flows through the resistor. Because C1 had already discharged to 0 volts before V1 and V2 were turned on, and the voltage across its terminals was 0, you see that the current flows down the moment V1 and V2 are turned on. So does the current flow this way, or does it split between the two sides? Because at this instant, the voltage across C is 0. Therefore, if current flows through the resistor, a voltage drop will occur, which contradicts the principle that the voltage drop is 0. Therefore, at the instant of conduction, the current flows only through the capacitor, and not through the resistor, meaning it is not limited by the resistor. So, what is the resistance of this parallel capacitor here? It's the initial strong current drawn at V1, V2. At the instant of conduction, the current flows through it, unrestricted by the resistor, allowing the current to rise relatively high. Then, as this current flows through the capacitor is gradually charged, and the voltage gradually increases before current begins to flow. Ultimately, it's the current limited by R. So, if you look at the diagram here, where does the initial pulse come from? It comes from this device. The current initially flows through the capacitor and is unrestricted, hence this strong initial pulse. As the capacitor charges, the current gradually increases, the resistance is limited, and the current decreases. Its function is this. So, in reality, while the ideal waveform may seem quite complex, actual circuit designs are often simpler. However, the simpler the circuit, the more difficult it may be to understand. Okay, let's continue with GTO-GTR. I won't repeat the conceptual parts that everyone can understand. It's not that they're unimportant or that you shouldn't know them, but I think everyone can understand them. We'll only talk about the things that might be difficult for some to understand. The textbook gives a circuit diagram of a GT group drive circuit built with discrete components. In this circuit diagram, I think the only thing that might be hard to understand is this compressed circuit. So, let's talk about this part of the circuit. Take a look at this circuit. This circuit has a transformer. The transformer is tested on a primary frequency and on a secondary frequency. The primary frequency is marked as 50 kHz. It's either a typo or 50K words. Why is the frequency so high? Everyone has seen the paragraph under the title of Chapter 8, previewed it, and studied it. There's a sentence there based on knowledge from electrical machinery. The higher the frequency, the smaller the transformer needed to transmit the same power. The reason for increasing the frequency by 50 kHz is to reduce the size of the transformer. Now that we know this, let's look at the secondary winding of the transformer. There are two windings, N2 and N3. The textbook clearly states that after winding N2, a half-wave rectifier circuit consisting of VD1 and C1 is used to obtain a 5V output voltage across C1. This statement assumes that the long straight line connected to the common terminal is called D. Therefore, the voltage across C1 is 5V. Now, consider this. If the voltage across C1 is 5V, so, if the N-terminal of this secondary winding has alternating current, AC, at both ends, and it also has AC, like the sine wave I drew above, what is the amplitude of this sine wave? We've learned about this kind of rectifier circuit in analog electronics, and we understand it even better here. We know we don't need to consider the subsequent discharge, because discharge is instantaneous. We connect a capacitor to the back of this diode to stabilize the voltage. The voltage across this capacitor should reach the peak value of the AC power supply voltage, until it reaches that peak value. Therefore, the voltage across C1 is 5 volts, meaning the peak value of the secondary winding voltage of the sine wave obtained on the N2 winding is 5 volts, just like the 5 volts I marked here. Next, let's look at N3. Here, the structure is the same as above, with a diode, D4, and a capacitor, C4, connected. However, you'll notice this diode is a bit strange. Its orientation is reversed. What is that? This is also the difference between half-wave rectification and the above. The only difference is that the above rectification leaves a positive half-wave and removes a negative half-wave, so the output voltage is positive. The diode in this direction leaves a negative half-wave and removes a positive half-wave. The gain rate is also half-wave rectification. Because it is negative half-wave rectification, the voltage across C4 is negative -15 volts relative to the same voltage across B. Since it is -15 volts, which is 5 volts, the number of turns of N3 must be 3 times that of N2. Its peak output sinusoidal voltage is positive -15 volts. Okay, now that we've covered these basics, let's look at the so-called pressure-driven hydraulic rectification mentioned above. This refers to this part. As described in the textbook, after this voltage multiplier rectification, the voltage obtained across the capacitor C3 is positive 15 volts. What does being suppressed mean? This secondary winding refers to a winding where the peak voltage is only. However, you've obtained a positive 15 V output voltage using this 5 VAC power supply. This is a voltage doubler rectification, effectively doubling the voltage. In fact, it's tripled. Now let's figure out why it's 15 V. To understand this, I've marked a few points here. As I mentioned earlier, this wire is D1, and everything is referenced to it. I've marked a blue dot and a red dot. Please look at the blue dot. Since we've already said that the voltage across C1 is positive 5 V, this point is 5 V higher than this point. Therefore, given that this diode is B2, what should the voltage at the blue dot correspond to? If the diode is the anode of the second diode, that's 5 volts. And the cathode, well, that blue dot must represent what voltage? Diode? When the anode potential is higher than the cathode potential, it will lead to. So what exactly happened? The blue dot has a voltage of 5 volts. This is the first option. The second option. The potential of the blue dot will never be lower than 5 volts. Of course, both of these statements assume an ideal device and neglect the diode as a secondary consideration regarding the forward voltage drop. Which would you choose, A or B? Is there a difference between the two statements? Let me repeat. A. The potential of the blue dot is 5 volts. B. The potential of the blue dot will not be lower than 5 volts. Do you feel there's a difference between these two statements? B's statement that it is no less than 5 volts implies that it could be even higher than 5 volts. And A's statement confirms that it is 5. Everyone should choose the so-called unidirectional conductivity of the B2 diode. As long as the anode potential is higher than the cathode potential, it will conduct. Therefore, the statement about B does not violate the operating characteristics of a diode. If the anode potential is higher than the cathode potential, it will conduct. Can the cathode potential be higher than the anode potential? It's not said that it can't, right? So, if you're asking about the cathode potential of a diode connected here, the only answer you can give is B. Because A is uncertain, B is certain, and B includes A. After saying that, let's look at this capacitor C2. C2 will obviously be charged, and you'll notice that there's no resistance here. So it must mean something. One end connects to the blue dot, and the other end connects to the red dot. The red dot is actually the terminal of the transformer's secondary winding N2. Here, the transformer acts as a voltage source. Therefore, since there's no resistor to limit the charging current, the voltage across the capacitor at any given moment will be the voltage difference between the red and blue points. Any difference will cause it to charge extremely quickly, and the voltage across the capacitor will become this difference. Now, I have a question for everyone. How much can this capacitor be charged? And after charging, is its voltage positive on the left and negative on the right, or negative on the left and positive on the right? It has already been stated that the blue dot potential will absolutely not be lower than 5 volts. If it is lower than 5 volts, it will conduct. So the voltage across the capacitor depends on the red dot. And what's the significance of the red dot? You see, this line shows the voltage on the DN2 winding. We've already drawn it. It's the voltage at the red dot. Alright then. In this situation, both the blue and red dots are known to answer my question. Will capacitor C2 overshoot to what voltage? Is it left positive and right negative, or left negative and right positive? Everyone agrees that the left side is negative, and the right side is positive because the potential of the blue dot is no less than 5 volts, which is the highest possible value. Therefore, the charge must be negative on the left and positive on the right. This is certain. So how many volts? You see, the voltage at this point is a sine wave, the highest being 5 volts, and the lowest being 5 volts. Okay, let's walk through a store. Let's say it starts at Wufu. So let's take a look. When the blue dot is powered on, there's nothing there. The voltage across the capacitor is 0. When the blue dot is below 5 volts, the diode conducts. Once the diode is fully conducting, the blue dot represents 5 volts, the same as the 5-volt mark. Therefore, the capacitor won't be charged, and the voltage across both ends will be equal. Then time begins to move down this path. Notice that the voltage at the blue dot will never be lower than 5 volts, while this one is already below 5 volts. At this point, the capacitor begins to charge. This is the voltage at the red dot on the left. The charging current should flow from blue to red. As a result of charging, the voltage across the capacitor should be negative on the left and positive on the right. As this process continues and time passes, the voltage decreases further and further, reaching its lowest point at 5 volts. So what is the voltage of capacitor C2 now? It's definitely negative on the left and positive on the right. At this point, doesn't that mean this end is 5 volts, and this end will never be lower than 5 volts? So if it's 5, then it's 10 volts, right? At this point, the voltage across capacitor C is 10 volts, with the left side negative and the right side positive, right? And if we continue like this, it will go higher. The temperature started to rise from the 5th day of the 5th lunar month. Please be careful as you ascend. It's currently at 10 volts. If the voltage increases, and if the 10 volts voltage remains constant, then it will also increase, right? It will eventually exceed 5 volts. A voltage higher than 5 volts is permissible. A voltage higher than 5 volts simply means the diode is not conducting. There's no requirement that it cannot exceed 5 volts, as we've already discussed. So in this situation, don't look at the back. If the tube behind is blocked, there's no discharge path. Ignore the rest and just look at this point up to the blue dot. Don't look at the right side. At this point, the capacitor is not discharging, so the voltage increase here will raise the voltage at the blue dot. So let's look at the second question. What is the highest voltage that the blue dot can reach? That means it was rushed to the 10th floor without a discharge circuit. Then, as the voltage was raised, it was also raised to the highest possible voltage, which was 5 volts plus 10 volts, or 15 volts. That's how I came up with it. This electron is just a 15-volt voltage being suppressed. Watch it again yourself. The key here is that firstly, the presence of the capacitor increases the charging voltage. Secondly, the orientation of these diodes restricts the direction of current flow. These circuits are all mature circuits. You can just use them whenever you need them. Okay, let's continue. Everyone, look up and take another look at this circuit. Here, 3 different DC power supplies are constructed, -15V at the bottom and 55V at the top. What's the purpose? It's to meet the so-called ideal model required when driving the GPU. GTO and GTR are both current-driven, meaning that what's truly effective is the current. However, to add current to its control terminal, you always need to apply voltage. Therefore, the ideal driving waveform it provides has both voltage and current. What's truly effective is that it's generated by applying voltage. So you first apply voltage, and the voltage generates current, and that's it. Why are these 3 different voltages constructed here? Let's explain in stages. First, isn't it called a strong pulse? First, let's apply the 15V that's been pressed out above. How do we apply it? Let V1 conduct 15V, that's it. Then, the flat section is provided by the 5V supply, and then the 2V supply is applied to the flat section. So when it's turned off, you just need to use the auxiliary food attachment as a 3-way valve. It's that simple. Then, for all power electronic devices, if you can apply a reverse voltage to its control terminal when it's turned off. What does better noise suppression mean? In our circuits from experiments 1 to 3, all the fat drive circuits have a high level, 12 km per hour, applied during power up and a 0 level applied during power down, so there's no response. This is because our circuits have low power, and the noise level isn't high enough to reach that level. However, at high power, if you apply 0 instead of reverse voltage when turning it off, it might generate some spikes. The spike amplitude is relatively large, which could cause the device to misconduct. Therefore, a safer method is to apply a reverse voltage during power down. What does applying a reverse voltage mean? It means that noise still acts on it. If you apply a reverse voltage, which is originally negative, and then add noise and 0, the amplitude will naturally be different. Therefore, applying a negative voltage is safer. So how is negative voltage applied here? It's because R3 and R4 divide the -15V voltage. After the voltage division, it's clamped on top. This is the reverse voltage applied. This is the safety measure in case of crown failure. This is GTO. Next, let's look at GTR. GTR is a little different. In Chapter 2.12, when we talked about GTR, we mentioned something in Section 2.4. You should still remember that the textbook mentions GTR here again. In order to shorten its turn-off time and speed up its response, we usually put it in a critical saturation conduction state when it is turned on. Critical saturation conduction means that it enters the saturation region, but only just enters the saturation region on the side of the boundary between the amplification region and the saturation region. If it enters the saturation region more deeply and is far from the amplification region, it is called deep saturation, sometimes also called oversaturation. This critical saturation occurs at the edge of the saturation region, making it easier to exit saturation when turning off. Therefore, the turn-off time is adjusted. The current problem we face is how to ensure that the GTR's drive circuit is in a state of critical saturation protection during its design. The function achieved without reaching deep saturation is what the textbook refers to as the so-called backside microcircuit. Let's explain what it is. It's actually quite simple. What is the backside microcircuit? It's a circuit where two diodes, D2 and D3, are of the same type, meaning their functional performance indicators are basically identical. So how do these two diodes allow the diode to function at critical saturation? The key point here is, look at this sentence. If you're talking about ensuring this device operates at critical saturation rather than oversaturation or deep saturation through circuit design, then you need a detection circuit with criteria to determine its current state. Through research on the characteristics of this GTR device, we discovered a key characteristic. When the collector potential is oversaturated or deeply saturated, it will be lower than the base potential. Conversely, when the potential difference between the two is not significant and is essentially equal, it is in a critical saturation state. Therefore, our circuit design goal becomes simply to ensure that the collector potential and base potential are approximately equal, which is called critical saturation. If the collector potential is lower than the base potential, then the device is definitely oversaturated, which is incorrect. You need to make it a component protection device. This is the first thing I can determine. What state is it in? The second thing is, even if it is already oversaturated, how do you make it critically saturated? What is controllable and can adjust this state? This is the second thing we need to decide. And what is this controllable thing? The magnitude of the driving current it actively injects determines the degree of saturation. Therefore, when you find it's oversaturated and want to bring it back to the critical saturation state, what's the solution? Reduce the driving probability. This means the drive current is too high and needs to be reduced to allow it to exit. Once these two issues are resolved, let's look at what this so-called shell-shaped microelectronics is. These two diodes have their anodes connected together. What does this mean? Think about what we just discussed about saturation. Oversaturation is when the collector potential is lower than the base potential. If the anodes are connected together and are the same type of diode, what does that mean? It means the second potential needs to be open, right? If the anodes aren't connected, do they have the same potential? The one with the lower cathode potential will be open, right? Now it's oversaturated, and the collector potential is lower than the first. Does that mean VD2 isn't open? Originally, when VD2 wasn't open, you could see the current flowing through VD3 and injecting into the base. Now, suddenly, we see a lower potential here, which must mean oversaturation. As mentioned earlier, how do we return to critical saturation when the current is too large? How do we reduce it? Doesn't this involve current shunting? These two paths are connected in parallel. The current flows through here. When it's not open, it flows through. When it's open, a portion of the current that originally flowed through it will be diverted here, injecting less current. This reduces the potential difference between the 2 points, allowing it to return from oversaturation to critical saturation, making the potential difference between them less significant. This is why the second potential is different. So, the state of these two diodes here is maintained at the critical saturation position by adjusting the magnitude of the electrode injection current. This is the so-called Becker circuit. Then, at the front end of this circuit, to the left of the Becker microcircuit, you'll see an R and C in parallel. This is the same RC structure as the one in the thyristor trigger circuit, used to form a strong pulse. We already know this, so we won't go into detail. Okay, 5-minute break. Let's get started.